Hello and welcome back to Unit 12 on rotational kinetic energy, torque, and equilibrium. In this part, we are going to look at three examples. One example dealing with net torque, one example dealing with rotational work, and one example dealing with conservation of energy, including rotational energy. Let's begin by looking at the example involving net torque. So here we have a pulley. This pulley has two masses hanging from it, M1 and M2. M2 hangs off of a little radius and M1 off of a bigger radius, and we're told the moment of inertia of the pulley up here. We're told the strings are light, so we don't have to worry about them. And this entire thing is going to accelerate. We want to know what is the direction of the angular acceleration of the pulley and the linear accelerations of the two weights. We are also given the radii and the masses that are hanging off of the pulley. To begin with, let's look at the free body diagrams of these three objects. Let's begin with mass 1. Mass 1 has, I'm going to call it tension 1 pulling up on it, and its weight pulling downward. Mass 2 has a similar free body diagram, tension 2 pulling upward, and its weight pulling downward. The pulley has two forces on it. It has tension 1 downward on the right out of the large radius, and tension 2 pulling downward on, I said that was the right a minute ago, on the left, and tension 2 pulling downward on the right off of the small radius. When working these sorts of problems, you need to think about the direction of motion. Mass 1 will move up while mass 2 moves down, or vice versa, and the pulley is going to rotate in this process, and you want to keep everything moving together. I'm going to assume that mass 1 will move downward, and therefore mass 2 will move upward. Because the tensions are off of different radii on the pulleys, these two are not going to move upward and downward with the same acceleration. Therefore, I have subscripted them with A1 and A2. The pulley is going to rotate as well. If mass 1 moves downward and mass 2 moves upward, that's going to give us a rotation that is counterclockwise. Now, remember that this is an assumed direction for the acceleration. We don't know what actually is going to happen. Those two tensions, however, will cause torques on the pulley. So let's define those torques really quick. Torque 1 will be due to tension 1, and that is going to have a radius of R1, a force of tension 1, times the sine of those two. Now, often I haven't written this sine term down because often when dealing with this sorts of situation, the angle is 90 and the sine of 90 degrees is 1, and it just goes away. Tension 2 will have a radius, or torque 2 will have a radius of R2, T2, and again it will be a sine of 90 degrees, which leaves me with R2, T2, and I forgot to put a subscript there, so we'll add it. Let's also think about directions. We're assuming that the pulley is going to rotate counterclockwise. If I think about using the right-hand rule, that means that tension 1 is going to be out of the page at me and tension 2 will be in. And to keep everything consistent, I'm going to let tension or torque 1 be positive and torque 2 be negative in that case. I'm now going to look at mass 1. the net force on mass 1 will equal its mass multiplied by its acceleration. The two forces on mass 1 are its weight in the direction of the acceleration, minus the tension 1 in the opposite direction. That equals m1a. That allows me to solve that T1 will equal m1g minus m1a1. And now I'm going to plug in the fact that a1 can be written in terms of the angular acceleration, alpha, times the radius, a equals r alpha. A similar analysis on mass 2 yields that tension 2 minus m2g equals m2a, or that tension 2 equals m2g plus m2a, and I can again plug in that that will be alpha times r2. I forgot subscripts, so I'm going to put those A's, 2's on the subscripts for the A's. I can now think about the net torque. That will equal I alpha. The net torque, as we discussed on the previous slide, can be written as T1 minus T2, given the directionality here, equals I alpha. T1 was R1, not T, sorry, tau 1 was R1 T1. Tau 2, the second torque, was R2 T2. That equals I alpha. And now what I'm going to do is I'm going to plug in the values for T1 and T2 that I got by looking at the net force. That gives me R1 times M1G minus M1 alpha R1 minus R2 times M2G plus M2 alpha R2, and all of that has to equal I alpha. I'm now going to distribute through the parentheses and rearrange the equation so that all of the alphas land on one side of the equation and all of the terms without alpha land on the other side. On the side without alpha, I have R1 times M1G and minus R2 times M2G. On the side with alpha, I have M1 alpha R1 squared, and then M2 alpha R2 squared. This allows me to plug in numbers and find that alpha equals negative 0.25 radians per second squared. Okay, so what does that negative mean? Well, remember back at the beginning, we assumed how this was going to move. We assumed that mass 1 would go down, mass 2 would go up, and that the pulley would rotate counterclockwise. The fact that this is negative tells me that alpha is actually 0.25 radians per second squared in a clockwise direction. So I chose backwards